All righty. And morning, and very happy to have you back in class. Certainly very excited to start our new adventures on doubly reinforced sections. But before we do that, want to finish a little bit off on the singular reinforced section still, okay? And like I said, you might want to start looking at the homework, especially this homework number 2 is very long and has a lot of questions, especially number 2, problem number 2, number 3. And we were talking about different levels of a reinforcement and how you can find the moment of resistance with different level of reinforcement. So that's a little bit involving. So if you haven't started yet, please, I beg you to start right now because you have questions. Okay. Now for the questions, let's discuss together tomorrow at 2 o'clock promptly using the same Zoom link for lectures. And if you don't see me there, just don't worry. Wait there for a couple of minutes because I'll see from email notifications somebody jumped in. I will jump right back in if I'm in the meeting or something. Okay. So that's for that. All right. Okay, so with that said, let's start today's lecture on some of the parts of the singular reinforced section again. Let me do share my screen and apologize for the technical difficulty last time we have. And I figured out the reason why because I have several Wi-Fi names and sometimes the iPad connected different ones. So sorry about that. Okay, but this should not happen again. I believe I fixed that. All right. Okay, so let's talk about the singular reinforced section. Okay, so starting off this lecture three, and still we're talking about singularly reinforced section. Okay, so singularly reinforced. Okay, but today we're going to focus on multi-layered reinforcement. Okay, multi-layers reinforcement. That is more than one layer reinforcement in the section. More than one layer reinforcement in a section. Okay. And again, I have to ask you to mute yourself so we don't hear background echoes from the recording. If you haven't done so, please do that. Thank you so much. And then talk about a singular reinforced section, right? So the definition of singular reinforced section is that we provide a tensile reinforcement, not a compressive reinforcement. That means if I say singularly reinforced section, it means that I have a section at the top part of the section take care of the compression from the concrete, and the bottom part I provide steel or reinforcement of bars to take care of the tension. All right, so this is called a singularly reinforced section. And when we talk about singularly reinforced section, and this is so-called single layer, okay? Single layer means I just have
Professor, are
one
we
row.
supposed to be seeing something?
Oh, you don't see anything now?
No, there's nothing.
All right,
Nothing happening.
let me do that again. So, okay. Can you see anything here right now?
Yep, thank you.
All right, no problem. Sorry about that. And then if I say I have a doubly reinforced section, I have not only one, I have a single reinforced section with multi layers. Not only have one layer reinforcement, I have multiple layer of reinforcement. All right. So this is called multi-layer, right? This is called multi-layered. All right. So we talk about this
It's
as
not
well.
changing.
It's not changing.
Now I can see your mouse, but your mouse cursor. But is there supposed to be something in the second rectangle? Because there isn't.
Might be some lagging issue. Can you see it now still? Can you see it?
No.
Nope.
All right.
It's like it's just the when you started sharing it updated your screen and then it never updated it again.
All right, let me try it again. I think it frozen sometimes. I never had this trouble last semester with this. Is it changing now?
Yes.
Try
Okay.
writing something.
Okay, can you see a wiggle?
Yes.
All right,
Yes.
good deal. Okay. All right, well, I got to be a little bit more sensible with this technology. Seems like I thought we were very advanced. Apparently not yet. Okay. Thank you for reminding me. All right. Okay, good. And let me know whenever you see something frozen or not. Okay. Let me just try to be careful with this thing. Okay, thank you, by the way. Now coming back, right? So we talk about this is single layer and this is multi-layered sections. The difference, right? The difference is that, hello?
Lay down.
Hello? Okay.
I
Like
think
I said,
someone's talking to a pet.
all right, okay. So let's try to mute it. I don't mind talking to your pet, but I still have to think a little bit, so sorry about that. Okay. So coming back to this, we have single layer and multi-layered. The main difference is on the left-hand side, right? The main difference is that for a single layer, I have dt equal to ds. All right. On the right-hand side, I have dt not equal to ds. I have a dt not equal to ds. Okay. Okay. So that's the major difference. That's the major difference. All right. So still got some background noise, but anyway. So for this, for multi-layer reinforcement, right? For multi-layer reinforcement, I just want to emphasize on that. We need to be able to find a group of bars, right? The group of bars, center of the group of bars. So to do that, we now know that this is roughly where the center's at. This is roughly where the center's at, okay? And also we also know that I have to use my first moment or static moment to find the distance, right? So if this is first layer, and I have the distance between the first layer to the bottom reference line, okay, I call it D1, and the second layer is right here, okay, and this is distance D2, all right, and of course I have area for the first layer is called A1, area for the second layer is called A2, all right, so if I want to find out the distance between the center of the group of the bars to the bottom here, so let's call it D, or in this case, matter of fact, it's not D, so to speak, it's Y bar. So the equation goes like this, which is Y bar equal to sigma AI DI divided by AI. Okay. All right. So with that, if you want to find the exact location of depths, right? So the depths of the bars, okay, is gonna be right here to do an extension, and then from the top, that is the depths. That is the depths, and so depths d, and mind you that this is ds, okay? Mind you that this is ds. The depths ds equal to the height minus y bar. All right, and naturally, you know that in this case, the last layer of the reinforcement, right? The last layer reinforcement and the depth of that, of the last layer reinforcement, this is dt. This is dt. So that is difference between the single layer and multi-layered. And we have gone through the multi-layered. All right, so today, let's continue this and talk about one more example, right? Or maybe two more. So let's take a look at example on multi-layered, okay? Example on multi-layered section. Okay. All right. So first of all, let's take a look at the section, right? Let's take a look at the section. I'm just gonna show you this. Hold on one second. Okay. All right. So I am going to have a cross-section, rectangular cross-section on the left. Okay. And with that, I have a width of 12 inch, very standard. Okay. And height of 24 inches. What we call it 1x2, right? And now I have bars, first row at the bottom here, 4 number 9 bars, okay? 4 number 9 bars. All right, and I then have a second layer which just have 2 number 9 bars. All right, and quickly when you see number 9, you immediately realize that number 9 have 1 inch squared of cross-section area, right? That comes in handy, okay? And then my purpose first is trying to find out the center of the bars, And by the way, the distance between a position between the bars is that this is here, okay? This is one of the concrete covers, and this is another distance, Okay. Now to save time, let's make it simple for now. Let's just say I already know the depths. Save you the calculation. Okay. Let's just say I already calculate this out. This one to be 16.8 inches. Okay. 16.8 inches. And by the way, sorry, this is not 24. Let me get this correction. This is 20. Okay. And the depths of the bars, which is the last layer reinforcement here, dt equal to a 17.5 inch. All right, so that's all the geometry we know right now with the section. And for the input materials wise, we're using 4KSI concrete. Okay, and also using grade 60. All right, so when I say grade 60, you immediately realize that means the yield strength of the bars are 60 KSI. Okay, so that's all the cross-sectional detail we need to know to compute, right? To compute what? We're trying to find out Mn and phi. Okay, and if you forgot, phi is so-called the stress reduction factor, right? Stress reduction factor. So let's solve this thing, right? Let's solve this thing. So let me just switch back real quick. So solve. Okay, step one, right? So what is step one? I need to find my actual compressive zone A. Okay, and with that, I can compute my first effective compressive zone A, and then actual compressive zone C, and then the strain in the steel. Okay, and now when I do this, I always assume the steel yield. Assume reinforcement bar yield. Okay, and we're going to come back to check whether the yield or not. Okay, we're going to come back and check whether they're yield or not. But for the effective compressive zone A, that is beta 1C, and that has to equal to ASFY, which is the tension from the steel, divided by 0.85 F prime C, which is compressive strength of the concrete, and B, which is the width of the concrete. Right? So you bring the number, so I have 6 bars. So now this gives me a 6-inch squared. And I use the steel, which is 60 KSI, grade 60, and divide by 0.85 F prime C. Now in this case, it's 4 KSI, and the width of it is 12 inches. And you do the calculation, you find out this is 8.82 inch. Okay, 8.82 inch. All right, and then I have C equal to A divided by beta 1, and that is about 10.4 inch. 10.4 inch. So how do you know that? How do you know that? Because, right, I already know beta 1 equal to 0.85 for F prime C equal to 4 KSI. Okay, right, so that is the Winnie stress block coefficient. Now with this, I can check the strain in the steel, and if you remember, we talked about this, right? And this is actual compressive zone C, and bottom here is the steel, and this is DS, okay? Mind you, this is DS, all right? So when I say I want to check the steel first, right? I can also check for multi-layer reinforcement. I can also check, and this is epsilon T. Okay, and this is use dt. All right, that's the difference. So now if I want to check, I say epsilon T, which is the last layer of reinforcement. Okay, last layer of reinforcement equal to dt minus C divided by C and multiplied by epsilon Cu. And in case you forgot, epsilon Cu equal to 0.003. That is the crushing strain of the concrete. So you bring the number in here. So dt now is 17.5 inch, and C we just calculated out is 10.4, and divided by a 10.4 and multiplied by a 0.003. Okay. Now with this, you got your tensile strain of the steel is equal to 0.002048. 2048. Okay. So this, and be careful, this is smaller than the yield strain of 0.003. 0.00207. So what happens? What happens is that this one does not yield. Right? We have a problem. This one does not yield. Okay. So what we'll do, what we need to do, because somebody say something.
Yeah, I have a question.
Yeah, go ahead.
Where'd you get the 0.200207 from?
That is what is that? Think about it. That is the
Is it
epsilon
the-
y.
So is it the yield, like the yield strength for, or you strain rather?
Well, what is epsilon y, right? That is the yield strain of the steel, right?
Yeah. So is that
So,
like always given then, or?
well, we talk about this. You need to remember this, right? This is almost
Okay.
like constant, right? And how do we get this number if you flip to previous lectures, right? So epsilon y should equal to the strength, yield strength of the steel divided by the Young's modulus of the steel, right? So what is the yield strength for grade 60, Louis?
60 KSI divided
Right.
by
What is
29,000 KSI.
That's right. So that's how you got this number of 0.0207.
Oh, all right. Well, thank you.
Sure, no problem. And be careful that don't be sorry, but this is a good question. Be careful this epsilon y changes when you have different grade. Okay. So let me just write down here. So this depends on the grade. Okay. For grade 60 is this number. For grade 75 it's different number. Okay. Be careful. All right. This is actually a good question. All right. Okay. So let's come back. Now the problem is it does not yield. The problem is it does not yield. And what we're gonna do about it? What we gonna do about it? Okay. So when I say it does not yield, it means that the strain in the steel is smaller. The strain is still smaller. What happens here is that at the beginning I assume the bar yield, right? So going through the process, where did I exactly use this assumption? So I used it here first. Okay, and what is that? That is basically tension from the steel. Remember, ASFY. So when I start doing this whole analysis, I assume that the steel yield, I use the yield strength of the steel to get my tension force. All right. Now, which in this case, I just proved that it does not yield. My assumption does not hold. So what I have to do is I have to go to step 2. Okay, this is new. I have to go to step 2 is to find the true tension force, right? Find the true tension force. And to find the true tension force, I need to find the true stress in the steel. I need to find the true stress in the steel. Okay. All right. So how do I do that? How do I do that? This is how. So tension force from the steel, T, steel equals to AS, which is the area of the steel, multiplied by the stress in the steel. Now the only difference is before I use Fy, now I cannot. I have to use AS, and this fellow here equal to the Young's modulus of the steel, ES, multiplied by the strain of the steel, epsilon S. Okay, now this I can write it out, ES, and what is the strain in the steel, right? The strain in the steel, we show that it is D minus C divided by C multiply epsilon Cu. Is that right? Right? So here I need to find my concrete compressive zone C to get my total tension T. Total tension T. But I really don't know that. I really don't know that. Right? It's a chicken and egg. I don't know that. I don't know that. So what am I gonna do? What I'm gonna do? Okay. So I'm going to set up the equation, right? I'm going to set the equation. I say I don't know exactly what is the compressive zone C in this case because the steel does not yield anymore. The steel does not yield anymore. So I simply say, you know what? Let's just do this. Let my tension, which equal to now AS, ES, and D minus C divided by C epsilon Cu, which I don't know the C yet, okay? Keep in mind, I don't know the C anymore, right? Not like before. And I let that equal to the compression from the concrete, and that is 0.85 F prime C, 0.85 prime C, beta 1 C, beta 1 C. Okay. So now what I need to do is I set this equation equal to each other. Okay, I set these two sides equal to each other, and I say, you know what? Let me just try different number of C. So I want to try C equal to 10.1 inch. Okay. In reality, you can try 10.4 like you just computed before, but I know the answer, so I'm just gonna try 10.1. Okay, so I already know the answer, but in reality, you have to do iterations. Okay, you got to do iterations. So when I try C equal to 10.1 inch, so happen to be that at C equal to 10.1, my tension equal to 346 kips. Okay, and my compression equal to 350 kips. Because at both sides I have C in it, right? I can figure it out. I can substitute the value in, and I say that this is almost equal to compression. All right, this is almost equal to compression. I say, hence, it is balanced. What balanced? Compression equal to tension, balanced. Okay. Now you may have a question. Say, Bob, you have left-hand side 346, right-hand side 350. How do you know when to call it? When to call they're balanced, right? So the rule of thumb is that always less than 3% errors. Okay, less than 3% errors. Okay. All right. Okay. So now with this, I can move on. I say now I figure out the actual compressor zone C equal to 10.1 inch. And this time, if I have C equal to 10.1 tension balanced the compression, on the moment Mn would naturally just equal to tension or compression multiplied by the lever arm. In this case, is D minus half A. Now this equation still stands. So tension now 346 kips. Okay. And now D minus A, what is D? What is D? And mind you here, this D is not DT, this is DS. Okay. This is DS, which is different, right? DS. Okay. So if you forgot, DS is right here. And we know that number from the initial setting of the problem that is given, which is 16.8 inches. Okay. This is given now, but in reality, you can calculate yourself. Okay. Calculate showed that before. And 16.8 inch is the DS, and minus 0.85, which is the coefficient beta 1. And don't forget a 10.1, which is actual compression zone C, divided by 2. Okay, and this eventually gave you a 4,350 kips inch, and you can divide it by 12 to get foot. That is 363 kip foot. And that is your nominal moment capacity, 363 kip foot. All right. Okay. So in case you forgot, right, you easily get lost in the details, right? We have assumed bar yielded and reached the conclusion does not yield, and come back, try to find out the equation, right, using the actual stress in the steel, and now try different actual compressive zones. This is try and error. Okay. This is basically try and errors. Okay. In reality, you can try a little bit more iterations, but eventually you reach a 3% difference between tension and compression. You call it balanced, and then you compute your moment capacity. Okay, and at the end, I need to find my stress reduction factor phi. Okay, I need to find my stress reduction factor phi, and in this case, for sure, because it does not yield anymore, right? My strain and always, right? Always, this is related to phi, so always the last layer, right? Always use last layer to determine the stress reduction factor. Okay, so epsilon t equal to dt, mind you, minus c divided by c multiplied by epsilon cu. And dt in this case is 17.5 inch and minus a 10.1 inch. By the way, compressor zone again was determined by trial and errors. Okay, and then multiply 0.003. And I got this number to be a 0.0022. Okay, this epsilon t. And again, this one 0.0022. You will find it a little bit interesting because this one does yield. It is yielded now. It is yielded now, slightly on the margin, but it yielded. Okay, so funny that the last layer yielded, but if you check the other layer or the group of a bar, they don't yield. They don't yield, meaning the top layer does not yield. Okay, the top layer does not yield, but that's fine. So I find out the last layer strain is epsilon t equal to 0.0022, and I want to use the equation phi for it. And if you quickly recall, right, in your head, I want you to have this image in your head that phi at lower strain is 0.65, okay, and this is below 0.0207. Higher strain 0.005, it is a 0.9, sorry, yeah, here you go, 0.9, and then linearly interpolate, right? So immediately you see epsilon t equal to 0.0022. That means that it's probably here in the middle. So I have to use that equation. That is 0.65 plus here, which is epsilon t minus 0.002, and multiply by 250 divided by a 3. Okay, and then plug in the number 0.65 plus this is 0.0022 minus 0.002 multiplied by 250 divided by 3, and you got the number to be a 0.67. Okay, 0.67, which is quite different from 0.9. All right, so now with that, I can say phi mn, which is the reduced, right, flexure strength or design flexure strengths. Okay, design flexure strength, and that is 0.67 multiplied by a 363 kip-foot, and this gives me a number 243 kip-foot. And you can see that this number is drastically small compared to the one without strength reduction factor. All right, what does it say to you? What does it say to you, right? So what we have done is we examined the section with multi-layer reinforcement. Okay, now we suppose have a stronger section because we add more steel to it. But the reality is, although you add more steel, it is less likely that your steel will yield. Hence, you have a bigger compressive zone, and then you end up with a smaller moment. Okay, why is that? Because I have a lower number of strength reduction factor and get me a lower moment capacity. All right, so I just want to keep in mind that whenever you design out there in the firm and in the company or whoever you work for, when you're trying to design a section, don't just blindly throw reinforcement in it to make the section stronger. All right, don't do that because it may not work sometime. It may not work sometime. So more reinforcement, I want you to remember this, more reinforcement doesn't always guarantee a higher capacity. Okay, does not always.
Hey, Professor.
Yes, sir.
So where does the 250/3 come from?
That is just in the equation. Have you reviewed the previous lecture notes? It should be there, right? That's part of the ACI equation. Okay.
Okay.
Yeah. You
Thank
might want
you.
to, yeah, you might want to take a look at the previous lectures. Okay. Thanks. All right. So this more reinforcement does not always guarantee high capacity is a key to this example. Okay. So just don't blindly throw reinforcement into it to expect high capacity. It may not always be the case. Okay. May not always be the case. All right. So now this is one example, and I want to give another example, right? Because multi-layer reinforcement is quite commonly seen problem. Okay. So let's just say example 2, another section. And now for this section, things are similar, but let me draw that out. So I have a width of the section, which is 12 inches again. And the height of it, let me increase that, hence a mistake I made earlier, which is 24 inches. And I am going to simplify my rebar configuration, just say 4 number 9 bars, 4 number 9 bars, okay? And then I say the cover at the bottom row, here is 2.5 inch, okay? And the input concrete is 4 KSI concrete, as before, and the yield strength of the bar is 60 KSI, okay? And now the question is, what is my MN? Okay, and what is my phi? Okay, now again, to simplify it, because I've shown you how to do it already, so I don't want to spend too much time on it. So I already calculated out for you. And again, the group of the bar have a center of ds, and the depth is dt. And we already calculated out for you ds equal to a 20.44 inch, and dt, which is the last layer of bars, equal to 21.5 inch. Sorry, sometimes this, okay. And then now we need to find out the capacity Mn and also stress reduction factor phi. So how to solve this problem, right? So we continuously solve, okay, like we said before, always step one, assume yielding. Assume yield, okay? Always assume yield first. And then compute the effective compressive zone A, C, and check the strain in the steel epsilon S. Okay, so how to do that? So A equal to ASFY, and this is where I use the yielding assumption, divided by 0.85 at prime CB. Okay, so bring the number in. So A equal to what? E equal to 4 inch squared. And how do you know that? You say, Professor, easy, right? So number 9 is 1 inch squared. Like I said, I love number 9 bars, right? You see a lot of it, so might as well remember it, okay? So 4 inch squared and multiply 60 KSI, all right? And divide by 0.85, and F prime C now here in this case is 4 KSI. Width is 12 inch, okay? And then you plug them all in and you find out your A, is actually 5.88 inch. Right? And immediately the actual compressive zone C equal to A divided by beta 1. And this is 4 KSI, so I know beta 1 is 0.85. And I know this number to be 6.92 inch. So that is C. Then again, I want to check my epsilon S, which is strain of steel. So let me just remove this to be consistent, okay? Check the strain of steel. So epsilon S equal to depth, now this is ds, okay? Minus C divided by C and multiply epsilon Cu. So ds we said is 20.44 inch, okay? And minus 6.92 inch divided by 6.92 inch and multiply by 0.003, okay? And now compute this out, and I got the strain in the steel equal to 0.00586. Now, I love this number. Why is that? Because this is big, right? This is not only much larger and than the yield strength of the bar, which is 0.0207, but back in my mind, I cheered a little bit because I know this is even bigger than 0.005. And why am I so happy? Because I anticipate the phi equal to 0.9, but this remains to be validated, right? I don't know yet. I'm just, have a feeling right here. Gut feeling tells me I'm okay. All right. And you say, why? You cannot determine that yet because in the next step, okay, I need to show that, right? Epsilon T strain in the steel last layer, right? To check phi, I need to use this, right? And that is dt minus C divided by C multiply epsilon Cu. Okay, because the last layer is deeper, so this number always end up bigger than epsilon s for sure, right? Always the case. So 21.5 inch minus C, now 6.92, 6.92 inch and divided by 6.92 inch and multiplied by 0.003, and I have this number to be a 0.0063. Okay, and that is much larger than the 0.005, and hence my phi equal to 0.9. And now I confirmed it. Okay, now I confirm the stress reduction factor is good, 0.9. Okay, got an easy case. Now with this number, I say, you know what? Now I feel full confident of finding my moment capacity or flexural strength, that is Mn equal to T d minus half a. And again, this d is ds, okay? Don't confuse yourself, right? Now Mn, continue to write it out. This is ASFY because yielded. This ds is what? 20.44 inches, right? So let me just write one more line here before I plug the number. So now I plug the number. This is 240 kips. Y is 4 inch squared, 60 KSI, 240, easy, okay? And then Inside DS is 20.44 inch, which is the effective depth, and minus 5.88 divided by 2. Okay, and then MN, oh, sorry, MN, that is equal to 4,200 kips inch. Okay, and in case you forgot, so I want to convert everything to foot, right? So 12-inch foot, and I have this to be a 350 kip foot. Oh, sorry, my write-up today is a little bit hasty. Kips foot. Okay. All right. So that is the nominal flexure strength. So last step, but not least, I want to find VMN, which is easy. So 0.9 multiplied by MN, 0.9 multiplied by 350, and that gives me 315 kip foot. Kip foot. Oops. Okay. All right. So this is second example. All right. Now let's stop for a second. Think about it. Okay. Think about it. Remember what we've shown before, what we have shown before in the previous example, right? So I'm just gonna draw a line here just to as a side note and compare, right? So previous example, as you've seen that the section looks like this, and it's 20-inch of depth, 12-inch of width, and I provide 6 bars. 6 bars, okay, quite a bit. 6 bars. And all of them are number 9, so this is 6 number 9 bars. Okay, and this is example 1. All right, and this we got moment capacity VMN. If you remember, we got about 243 kip foot. Okay, that's what we got. And now the other section, it's a slight higher or taller. Okay, slight taller. So this is about 24-inch, and this is 12-inch. Okay, and for this case, I only have 4 number 9 bars. Okay, so 4 number 9 bars. All right, and this is from example number 2, we just did. In this case, VMN written right here is 315 kip foot. Okay, what does that tell you? What does that tell you? It tells me that at least the taller, the better. Okay, the taller, the higher capacity. So it is easier to increase the design strength VMN by increasing height of the section. Then adding more bars. Okay. So whenever you are trapped into that the member is inadequate, what you want to do first is not just blindly throw the bars in, but to take a look at the structure to see if you can increase the section or not. Because that's always the safer way to go, easier, more effective way to go. Okay. All right. Okay. I'm gonna stop here real quick and want to ask any questions about this multi-layer reinforcement, flexure strength. Folks, anything for me in general or specific in details, anything that is not clear? Folks, are we good on this? Are we all sleeping? Okay, I got a 1 yes. Anybody else? Any questions? Good. Okay, all right, I got 2, so I'm just gonna move forward. Okay, I hope the rest of you guys are okay with this proposition. All right, okay. So now this has gone through the, let me just roll to the front end. Okay, this has gone through the singularly reinforced multi-layer. Okay, multi-layer, and we went through the single layer last time. Okay, multi-layer. So I'm gonna start a little bit lecture 4. Okay, I'm gonna start a little bit lecture 4, but we'll not get into the example today. Okay, not have enough time, but let's just say lecture 4. So okay, Lecture 4 is doubly reinforced section. Okay, doubly reinforced section. Okay, doubly reinforced section. All right, so now I've shown you how we're going to analyze, of course, this analysis first. Okay, we haven't talked about design yet. And so far, all we have done is given you the section, given you the reinforcement, and you went ahead, calculate the moment resistance. Okay, wasn't designed yet. Okay, wasn't designed yet. What is design? Design is give you nothing. You start from scratch, you know what is needed, and you come up with a geometry, and that is design. We haven't done that yet, okay? So be careful, okay, on the differentiation. So on the analysis side of it, first of all, again, let's run some comparison, right? Let's run some comparison. So I want to put on here conceptual of singly versus doubly. Okay, what is the difference between singly and doubly? So before I do that, I just want to draw the section, right? Draw the section out. Okay. All right, now assume I have bottom 2 bars here, and I call it AS, meaning they're tensile reinforced, right? Singly reinforced, and I have a depth of it, call it D. Of course, I can call it DS, but you know, it's D. All right, so I want to draw the strain distribution diagram. And I know that the concrete is going to fail at 0.003 compressive failure. All right, and I also know that if I have a singular reinforced case, right, this is where the steel is at. This is where the steel at. Okay, so we know this is singular reinforced cases. Okay, nothing surprise, and we know to do that you assume epsilon s, epsilon y, no big deal. But if I add another layer at very top in the compressive zone, okay, and I call this AS prime. All right, now imagine what happens. First of all, let's think about it. We said this before. Now ES over EC, which is Young's modulus of the steel versus Young's modulus of the concrete, roughly equal to 8. Okay, what does it mean? It means 1 inch of steel is as stiff as 8 inch of concrete, 8-inch squared of concrete. Okay, so meaning a little bit of compressive reinforcement can increase my concrete cross section a lot. Okay, a lot. So you can imagine if I put in compressive reinforcement in it, and mind you that I just set this depth to be ds prime, top to the center of the compressive side, ds prime. Okay, and the strain distribution will change significantly because I added more steel. So I will have a reduced. This is all by adding compressive reinforcement, okay? Compressive reinforcement. Reduced compressive zone. Okay, in other words, C drops. Okay, C drops. So if C drops, the actual compressive zone drops. I have a lesser compressive zone. Hence, the strain diagram will look like this because this is C. Let's call it C2 because this is adding reinforcement. Now comparing to without compressive reinforcement, this is C1. Of course, C2 is much smaller than C1. So now the strain epsilon S2 is much larger than epsilon S1. Meaning what happens? Meaning the increased strain in steel. Okay. Or epsilon S increases. Okay. Epsilon S increases. Okay. Now you say, oh look, this is pretty good, right? I decreased my compressive zone, increased my reinforcement strain. Does that mean the moment resistance changes, increases? Sure, you bet. So moment resistance or flexure strength, okay, flexure strength. It's the same thing, okay? Don't confuse. Increases, right? Increases. So Mn increases, but slightly. Not so much. Why is that? Because although the strain still increases, the yield strength stay the same. Though the tension force almost maintains. Okay, the tension force did not increase at all. All right, by reduce the compressive zone size, all you have done is lift up the total compression force from the concrete and increase the JD a little bit. But since the decrease or the reduction in compressive zone is not significant, hence the increase of the JD is not significant neither. So the moment capacity does not increase significantly. It's only a slight increase. I want to say this, okay? I want to say this. It's only a slight increase. All right, only a slight increase. Not too much, not too much. Why am I emphasizing this? Because you have this problem in the first exam, okay? You have at least multiple choice problem on this exam, okay? First exam. So I want you to remember adding compressive reinforcement, okay? Or we call it doubly reinforced section, okay? Okay, will increase Mn slightly, okay, but increase epsilon s significantly, meaning will increase the steel, strain in the steel significantly. And what does that mean? It means that hence increase the ductility significantly. Okay, so when I say what is the major benefit of adding compressive reinforcement, you say ductility. Let me put 2 squares on it, okay? So you remember it's ductility that is the benefits by adding compressive reinforcement. Not the moment capacity, okay? Not the moment capacity, but the ductility of the section, ductility of the section. All right, critical concept, critical concept. Okay, now you know the reason why we add compressive reinforcement into it. The reason we add compressive reinforcement in it is to increase the strain in the steel and the tension side of it and increase the ductility. All right, but not too much on the moment resistance. It's a slight increase, but not much. All right, so with this motivation though, we need to know how to compute it, meaning we need to know how to analyze a doubly reinforced section. So here is the section we just shown. So in addition to this tensile reinforcement AS prime, I also have compressive reinforcement AS, tensile reinforcement AS. I also have the compressive reinforcement AS prime. And the distance, again, for the compressive reinforcement DS prime, and the distance or the depth, again, for the tensile reinforcement is called DS. They're different, okay? Total height of the section is H, and the width of the section is B. Okay, so how do I analyze this section? We follow the same old rule. First, strain distribution diagram. Okay, remember the 20% partial credits from previous lecture? Okay, so we first join the strain distribution. So this is epsilon Cu for the concrete. Okay, and now I have a strain in the steel epsilon S here as before, but in addition, I also have compressive strain in the steel epsilon S prime. And now the actual compressive zone C is right here. Okay, so this is the strain. How about stress? So if I plot the stress, you know, from the Whitney stress block, that still holds, right? And immediately you can spot a mistake because the Whitney stress block should be smaller than the actual compressive zone C, right? So this is A, and now this is 0.85 F prime C. We talk about this, right? And then I have a total compression force from concrete. In addition to that, I have to add it one more, which is Fs prime, which is the stress, compressive stress in the steel. Now, on top of this, I then have Fs, which is the tensile stress in the steel, which is equal to Fy. Assume, right? Assume is yielded. And then internal force, okay? I have a CC right here, and not that distance from the top is half A. In addition to that, I also have a what? I also have Fs prime, and distance is ds prime. Okay, so I call this is Fs, which means stress. So I call this Cs in terms of forces, right? Cs, that means compression force from the steel. And then I also have the tension force at the bottom here. So this is called internal forces. Okay, this is internal forces. All right, so that is the new internal diagrams, right? Equilibrium diagrams for AA reinforced section. And just 1 minute, I'll let you go, okay? Now, with all this, right, what are the additional equations we have to consider? This? First of all, I need to draw my strain in the compressive reinforcement. So epsilon s prime divided by c minus d prime, ds prime, that is equal to epsilon cu divided by c. So this is how I calculate my strain in the compressive reinforcement epsilon s prime equal to c minus ds prime divided by c multiplied by epsilon cu. This is new, okay? This is a new equation. All right. Now, compression force from the concrete equal to cc. Before it's just 0.85 f prime c and beta 1, which is a and b. And now still the same. Didn't change. In addition to previous cases, I now have a compression force from the steel, which is AS prime, that is compression reinforcement multiplied by the reinforcement, multiplied by the stress in the steel in compression side, which is Fs prime. But, and listen to me, ladies and gentlemen, because we need to care for the concrete now. This is the added part. Why is that? Right? Why is that? So Bob, why don't you just write AS prime, FS prime? Now you have to minus or subtract a 0.85 F prime C. What does that mean? What happens? Okay. What happens is that when I compute my compressive reinforcement for the concrete, I assume it's a fully occupied section, means that there's no holes in the section. But in reality, I have actually two compressive reinforcement, meaning there's a holes in the compressive side of reinforcement. I have to take that out. Okay, I have to take that out. All right, so I want you to think about a little bit about it. And if you still have confusion, talk to me tomorrow, okay? But now Fs prime, which is compressive stress in the reinforcement top, equal to ES modulus of steel multiplied by epsilon prime. Okay, that is another thing has to remember. This has to be learned. So compressive reinforcement, this has to be less than Fy, means compressive reinforcement does not yield. So tensile reinforcement yield, but compressive reinforcement does not yield. And then last but not least is that total tension force has to equal to the compression force from the concrete, compression force from the steel, and to write it explicitly, ASFY, which still the tension side of it, equal to 0.85 F prime C beta 1 C B or A is the same thing, and plus AS prime, and this is from the compression side of S prime, Fs prime 0. minus 0.85 F prime C. Now that is the equation you need to compute the compressive zone. Okay. All right, so this is the concept of doubly reinforced section, okay? Okay, I want you to take a quick look at it and ask me a question. Now, today, I want to leave our first quiz. So quiz number 1, okay? This is additional, quiz number 1. I want you to repeat the same problem, but this is the section. So I have 24 inch. I have, okay, 1 layer of 2 number 10 bars, okay? And the concrete is 6 KSI. All right, I want to ask you that what is my, and this is grade 60, okay? What is my MN and what is my phi, okay? In the quiz problem on Canvas, you only need to input 2 numbers, right? You only need to input two numbers. I don't need to see the whole workout. I just want you to input this number and this number. Okay, and the width is 12 inches. Okay, be careful, 2 number 10 bars and L prime C 6 KSI. Okay, 6 KSI. So this is quiz number 1. I will open up on Canvas. You can fill in, and the deadline is a week, right? So deadline, okay, by next Monday. My write up by next Monday. Okay. All right. Okay. I'm done today. So welcome any questions. Okay. If you have any questions, stay behind so we can address them. All right. Thank you very much. See you on Wednesday.
Do we need